Excuse me. Okay, everyone, let's get started. For the last time, here we are in Math 152, Section 4. Professor Ellis, I am your SI Jack Work. And today our final topic of discussion will be power series and the use of complex numbers. Now, I'm going to preface this whole thing by saying that Taylor series, power series, and Maclaurin series in general are all very dense. For the most part, unless you're a math major, you probably won't be seeing them again. But it's important that we understand how they work. So let's take a look here. We know that a representation here, n equals 0 to infinity, c of x minus a to n, where a represents the center of our power series. Now, given that information, we want to find the radius and interval of convergence for a given power series. Now, let's say that our power series is given as summation n equals 1 to infinity of x to the n over 2 to the n minus 1. Now, how do we start something like this? Well, the easiest way to find this sort of stuff is to perform a ratio test. I'm sure you all remember the ratio test. We take the limit as n approaches infinity, the absolute value, and we replace all our n's with n plus 1, so x to the n plus 1 over 2 times n plus 1 minus 1. And multiply that by the reciprocal of our original, so we'll have 2 to the n, 2n minus 1, excuse me, times x to the n absolute value. All right, so we recognize some pretty obvious simplifications. X to the n plus 1, the n is gone, we're just left with x. Now we're going to have to play with the 2 to the n minus 1 a little bit, so let's continue writing this out in more simplified form. We have the limit as n approaches infinity, absolute value of x times 2n minus 1 all over 2n, and then we'll have 2 times 1 is 2, minus 1 is 1, so 2n plus 1. Okay, now we can do this with series limits from function limits, but to save us on writing, I'm just going to remind you that when we have n approaching infinity, we have 2n, highest power of n is to the first, so we take their coefficients, 2 over 2 is going to be 1. So this limit of n, as n approaches infinity, is x times 2 over 2, which is just equal to x. Okay. So now we need to remember how our ratio test worked, because we're trying to find where this converges, what values of x this can converge for. Since x is the only parameter, all we need is for x to be less than 1. Now, given that our terms of x are simply x, there's no x minus a, we know that our center a is equal to 0, which means, excuse me, if x has to be less than 1, our radius of convergence will be equal to 1. So that's part of our answer there. And then using our center of 0, we know that our interval of convergence is going to be negative 1 less than x less than 1. Now we're not quite done yet because we are unsure of our endpoints. The thing that you have to watch for in these problems is you can't assume what's happening at the endpoints. We have to perform tests. So we go back to our original series and we take approximation n equals 1 to infinity. And this time we're going to plug in our endpoint for x. So in this case we have negative 1 raised to the n over 2n minus 1. Okay. So what's going on here? What's going to happen with this series? Well, we have negative 1 to the n, which means our terms are going to be alternating, negative, positive, negative, positive. So we think immediately, all right, let's check for alternating series. Now, we already know that it's alternating, so now we just need to know that it's decreasing. So we would say that 1 over 2n minus 1. Okay, and now we'll replace it. Now we replace n with n plus 1, so we have 1 over 2n plus 1. Okay, and now we replace now we replace n with n plus 1 again, so we'll have 2n plus 1, 2, 3. Okay, so we have an increasing denominator. An increasing denominator denotes that our are getting smaller, which means this is a decreasing series. And by alternating series test, if it's an alternating series, negative, positive, and if the series is decreasing, then this portion converges by alt series test. Okay. Now, test our other endpoint. 1 to infinity, 1 to the n over 2n minus 1. Now, 1 to the n is just going to be 1 forever, so we can rewrite this as 1 over 2n minus 1. And there's no real obvious tests going on here. It's not a geometric series. So in this case, we're probably going to need a comparison test. So let's see here. 2n minus 1 is going to be greater than n for all values of n greater than 1. I can confirm that for you. We plug in 2 here. This is 3. This is 2. Plug in 4. This is 7. And this is 4. Just going to follow the same trend. So now we can look at 1 over n. 1 to infinity. And that's just the harmonic series, which we know from experience diverges. And because 1 over 2n minus 1 is going to be less than 1 over n, and 1 over n diverges, we know that sigma n equals 1 to infinity of 1 to the n over 2 to the n minus 1 diverges by comparison. Just write the comma here. Okay, so now we finally have our final answer. We know that negative 1 is going to be less than or equal to x is going to be less than 1, which makes our interval of convergence negative 1 to 1, and our radius, as we call it, is just equal to 1. All right. So as you can see, quite a bit of work for not a whole lot of problem. It's just the sort of thing we have to get used to with this stuff. So now let's do the same thing. This time our series is going to be sigma n equals 1 to infinity of x to the n times 3 to the n. So yet again, the way to find this is just to do the ratio test. Limit n infinity x to the n plus 1 1 over n plus 1, 3 to the n plus 1 times 3 to the n over x to the n. All right, a lot of obvious simplification here. X to the n is gone, x to the n is gone. We're just going to be left with x. 3 to the n is gone, 3 to the n is gone. We're just going to be left with 3 to the first. So this simplifies to the limit as n approaches infinity, the absolute value of x over 3 times n over n plus 1. Now the n over n plus 1 portion of this is, again, very easy to find. N approaches infinity. N over n, coefficients of 1, so this is just going to be 1, which means x over 3. That has to be less than 1, which makes our radius of convergence equal to. Yet again, we know that a equals 0. So our interval of convergence is going to be -3 less than, well, -3 less than x less than 3. And again, we have no idea what's going on with the endpoints, so we got to take a look. We plug in 3 to the n over n times 3 to the n. Those cancel. We're left with 1 over n, which yet again is just the harmonious series, which means that portion diverges. And page here, we take -3 to the n and 3 to the n, which becomes -1 to the n times 3 to the n, and 3 to the n, cancel. We have -1 to the n over n, which is the alternating harmonic series, which we know converges. So our final answer, we will have inclusive -3, exclusive 3. Radius of convergence equal to 3, and there we go. A little bit straightforward that time around. Just had some nice cancellation. All right, now we're going to jump a little bit into complex numbers, just because it's the last thing we learned, and it's not terribly important, but you'll have to know it for future courses. It probably won't be a big portion of your final, but let's say that we have A is equal to 8 minus 7i and B equal to 3 plus 4i. And given these two complex numbers, we want to find A plus B, A times B, A divided by B, and modulus. All right. So first couple aren't too terrible. We'll have 8 minus 7i plus 3 plus 4i. Just add your common types of terms. We'll get 11 minus 3i. Solution to A. Very simple. Just look at the terms, add the ones that are in the same position. Simple addition. All right, now A times B is going to be 8 minus 7i times 3 plus 4i. And you can just FOIL this one. So 8 times 3 is 24. 3 times 7 is negative 21i. 4 times 8 is positive 32i. And 7 times 4 is negative 7 times 4 is negative 28i squared. Now, remember, I is equal to the square root of negative 1, which means I squared is going to be equal to negative 1. So, negative 28 times negative 1 is positive 28. We can add it to the positive 24. That will net us 52. And then 32 minus 21, 9, 10, 11. So that is plus 11i, I believe. Yes, plus 11i. All right, that's the result of our multiplication. So multiplication with complex numbers is relatively straightforward. You just FOIL it like you would any other polynomial. And then once you've done that, the answer becomes relatively clear. All right. So now let's move to C, part C, which is A over B. That's going to be 8 minus 7i divided by 3 plus 4i. Now, what do we do about this one? Well, remember, we take the, what was it called? Conjugate. Take the complex conjugate of the denominator and multiply it by the complex conjugate over itself, which is the same thing as multiplying by 1. And then you just FOIL it out, and that's your division method. So in the numerator, we will have 24 minus 32i minus 21i minus 28 plus 28i squared. Okay, and then in the denominator, we will have 9 plus 16. Yeah, okay. Because that's just going to be negative 16 times I squared. I squared is negative 1, so positive 16. All right, so we can simplify this one. We'll get negative 4 over 25 minus 53i over 25. That's the answer to part C. All right, so this one, you just have to remember to take the complex conjugate. Don't try to divide like you would multiply, because it's just not going to work. But if you remember to take the complex conjugate of b and multiply by that over itself, relatively straightforward. Okay, so now we want to find the magnitude of A. So magnitude of A, which is just going to be equal to, how we find magnitude in typical sense, we'll have 8 squared plus 7 squared, square root of 64 plus 49, square root of 113. And it should be pretty clear where that comes from. We just take A, which is 8 minus 7i. We take the A and the B, we square both, we add them, and take the square root. Basically, how you would find the hypotenuse in a right triangle, how you would find the magnitude of a moment. Magnitudes really don't change across complex versus real fields. All right. So now we're going to try representing series, representing functions with power series. It's important to remember that 1 over 1 minus x is equal to sigma n equals 0 to infinity of x to the n for absolute value of x less than 1. Okay, so just going to perform some simple manipulations on this. I just want you to see the correlation here. All right, let's say we're given f of x equal to 3 over 1 plus x to the third. All right, now how do we represent this as a power series? Well, we just perform any operation that we performed to get from our original format to this new format, and we do the same thing to the other side of our equation. So we can see we multiplied by a 3 in the first place, so we'll have sigma n equals 0 to infinity of 3. And now, instead of minus x, we have plus x to the third. Now, this could be rewritten as 1 minus negative x to the third. Okay? So, now we'll just take the negative x and plug it in where our x will be. So we'll have negative x to the third to the n. Now we can simplify this a little bit, but for the most part, that's as far as we can go. What we can do now is say sigma n0 to infinity of 3 times -1 to the n times x to the 3n. That's the simplest form of our power series representation of the given function. Okay. Now, I think I have one more for you. So, let's say we have f of x is equal to e to x. And we want to find the Maclaurin series. Now, what is a Maclaurin series? The Maclaurin series is the Taylor series representation of the function where the center A is equal to 0. Okay? So, knowing that, let's look at f of x and let's check out f prime of x. F prime of x is equal to ex. F double prime of x equals ex. F triple prime of x equals e to the x, and so on and so on. Now, what does this mean? Well, this means that f of n, the f nth derivative, if you will, is going to be equal to e to the x. Now, we use this information in creating our power series because when we take our Maclaurin series, we want f to the n of the 0, which is just going to be e to the 0 or 1, which means our power series doesn't really change at all. We just have Taylor series, x to the n over n factorial. No change, no movement, just a standard. So that's really just a standard Maclaurin series right there. Now, real quick, see if you remember how to find the radius of convergence. What change for any given series, assuming it has x involved in it. So, yet again, limit as n approaches infinity of x plus 1 over n plus 1 n factorial over x to the n, x to the n, cancel, n factorial, n plus 1 factorial, cancel. The limit as n approaches infinity of x over n plus 1, which is just going to 0, because we're left with terms of n, they don't cancel out, regardless of what x is. The denominator is just going to keep getting bigger, so we're going to 0. Well, that means that our radius of convergence is equal to infinity, or negative infinity is less than x is less than infinity. Basically, x doesn't matter. This thing is going to converge everywhere no matter what your value of x is. You could plug anything in for x and still going to get exactly what you're looking for. All right, so that's all I've got today. Been a pleasure working with you all. Hope to see you again sometime. If you have any questions, feel free to ask. But beyond that, I think we're clear.